Hello and welcome to Lecture 2 of our Essentials of Semiconductor Device Physics course. In this lecture, we begin our introduction to statistical physics, dealing with the notions of systems and states. So we begin by stating this funny principle. The state property of a macroscopic system in equilibrium is always the most probable. This principle captures one of the most fundamental ideas of statistical physics, and our first job is to understand the meaning of this principle. But before we understand the meaning of the principle itself, we need to understand the meaning of its key terms. So in this lecture, we're going to cover the meaning of the term state and of the term system, and we're going to begin with system. So system is a word denoting everything we are interested in, everything we want to study. So for example, suppose that we are interested in studying a gas of particles. In this case, all particles of the gas and the container will be our system. And also, if the external environment is affecting our gas, then we have to include the external environment as being also part of the system. So system is only a word denoting everything we are interested in, including everything else that may affect what we are interested in. Now let's turn our attention to the meaning of the word state. So state is a synonym for condition. And in physics, we say that we specify a state of a system when we have sufficient information to be able to predict the evolution of the system. So, for example, let's suppose that we have the particles of a gas again. And let's suppose that the physics of these particles are governed by Newtonian physics. So to be able to predict the evolution of a Newtonian system, we need to know the initial conditions. So that means that to specify the state of the system, in our example, we need to specify the positions and the momenta of all particles in the gas. So each possible combination of positions and momenta of all particles specifies a different state of the system in this example. And we can also speak of properties of state. So a property of a state is anything that we can deduce once the state has been specified. So we will be interested in two main properties in this course, but for now we're going to focus attention in one of them, which is the energy. So if we know the state of a system, we can deduce the energy of the system. So energy is a property of state. In our example, to specify the state of the system, we need to specify the positions and the momenta of all particles of the gas. And if we know the positions and the momenta, then we know the energy of the gas, which in this example will be the sum of the energies of all particles of the gas. Now to make this example a bit more concrete, let's suppose that these particles have charge. So if these particles have charge, then the most significant potential energy is Coulomb's potential energy. And this is the expression for this kind of potential energy. You don't need to worry about this expression. The only reason I am using it here is to emphasize that once we have specified the positions, then we have specified the potential energy. N here is the number of particles we have. I and J are index for the particles. Q are the charges, and these are the position vectors. So when we have specified a state, we have specified all of these position vectors, so we have specified the potential energy in our example. And likewise, once we have specified the momenta of the particles, we have specified the kinetic energy. So this expression here is the kinetic energy P is the momentum of the particle I, m is the mass of the particle I, and this is the sum over the kinetic energies of all particles. So once we've specified the positions, we've specified the potential energy. Once we specify the momenta, we specify the kinetic energy. In other words, if we specify the state, then we know the total energy, which is the sum of the potential and the kinetic energies. Okay, so we've just seen that energy is a state property. And once we have specified the state, we have specified the property, we have specified the energy. So each state has a well-defined property. If you know the state, we know the energy. But notice that more than one state can have the same property. For example, let's suppose that all particles have the same charge and that we compare two states where all particles have the same positions and same momenta, except for these two particles where we keep their momenta but swap their positions. So these are two different states, because in one state this particle is here and in this state this particle is somewhere else. And the same for the red one. But they have the same energy. So this is an example of two states having the same energy. And in principle we can have lots of states having the same energy. So we need to keep in mind that more than one state can have the same property, the same energy. This is relevant to the notion of equilibrium that we're going to discuss in the next lectures. Now suppose again that we have a state specified in our example system. And suppose then we focus attention on this particle here. We could change the state by moving this particle in a continuous manner. In other words, we do not need to move the particle in discrete steps. We can move it in a continuous fashion. So that means that there is a continuum of states that we can access in this example. And this is a feature of classical systems. So in classical physics, states and properties, they form a continuum in the sense that there are always infinitely many states between two states. For example, we could consider a state where the particle is here, another one where the particle is here, and between these two there will be a continuum of states where the particle is anywhere between these two supposed particles' position. So in classical physics, states and properties form a continuum, and this is pretty obvious when we are discussing a classical system, but I need to emphasize it here because that's not the case in a quantum system. And in this course, we are actually interested in quantum systems. Now, to gain further insights into this difference between classical and quantum states, let's suppose that we have, as an example, a U-shaped potential, like a skate ramp with a ball inside. So this is an example of a classical system where the position and momentum of the ball specifies the state, and the height specifies the gravitational potential energy, and the momentum specifies the kinetic energy. So once we have specified the state, position, and momentum, we have specified the energy, the property. So ignoring friction, in our example, we know that if we drop the ball from a height h, then the ball will oscillate, accessing a continuum of states, because it will access a continuum of positions and momenta, and all of these states will have the same energy. But we could also access a continuum of energies, because we could drop this ball from any height h we choose. So I've concluded one more time that there is a continuum of states and properties that can be accessed by our example system. Now this is no longer the case in a quantum system. In a quantum system, it is often the case that states and properties are discrete. So that is as if we were only allowed to drop the ball from a discrete number of heights. And since the height we drop the ball from determines the energy, in this example, it is as if we were only allowed to access a discrete number of energies. But of course, there are no balls in quantum systems. In quantum systems, the particles are described by wave functions. So this is only a pictorial way of representing the difference between discrete states and states forming a continuum. Now we need to focus our attention on understanding the physical origin of the discretization of states. And the first important feature to notice is that the discretization of states is not peculiar to quantum systems. It is in fact a feature of any confined wave system. And a quantum system is an example of a wave system. So the discretization of states will happen every time we confine a wave, any kind of wave. So we can show the physical origin of the discretization of states using a more familiar system, like for example a guitar string. So we're going to assume a guitar string in our exposition of the physical origin of the discretization of states. Okay, so we're going to assume a guitar string to show the physical origin of the discretization of states, and we're going to show this origin using two different points of view. We're going to begin using a more mathematical point of view, and then we're going to discuss a more phenomenological point of view, which I find to be more intuitive. But let's begin with the mathematical point of view. Let's suppose we have a guitar string, and this string is confined between the point 0 and L, and psi of x is the function describing the dependence of the string height on space. So to know what is psi of x, in principle we need to know what is the wave equation describing the propagation of waves in this system. This wave equation, of course, exists. It comes ultimately from Newtonian physics, but we do not need to know the specific form of this wave equation to know what is psi x, as long as this wave equation is linear and space invariant. If we know beforehand that the wave equation is linear and space invariant, then it follows that this function, psi of x, must be given by a linear combination of a sine and a cosine function. In other words, if the wave equation is linear and space invariant, which is indeed the case, then psi of x is given by a sum of a sine function and a cosine function. This term k is usually called the wave number or momentum of the wave, and a and b are constants that we need to find by applying the boundary conditions of the problem. Now, if you want to know more about why we can know a priori that psi of x is of this form, if we know that the wave equation is linear and space invariant, then I recommend this book, which deals with linear and time invariant systems, but it's the same idea, only using time instead of space as the variable. Okay, so now let's apply the boundary conditions to the problem. Since the wave is confined, we have two boundary conditions. The height is 0 at the origin, so it is 0 at the point x equals 0, this boundary condition, and it is 0 again at the point L, so this boundary condition. So it's important to notice here that the fact that the wave is confined is manifested mathematically in these two boundary conditions. Okay, so let's begin with this boundary condition. When we apply this boundary condition, we want to evaluate psi at the origin. So we get 0 here, 0 here. Sine of 0 will be 0. So we end up with b times the cosine of 0, which is 1. So that means that psi evaluated at the origin is equal to b. Since the boundary condition requires that psi evaluated at the origin is 0, it follows that b must be equal to 0. So from the first boundary condition, we concluded that psi of x is reduced to this form. It is a times the sine of kx. Now let's see what happens when we apply the second boundary condition to the problem. Now we require that psi evaluated at the point L is 0 because the wave is confined. So that means that a times sine kl is 0. So there are only two ways that this function can be 0. One way is if a is equal to 0, but that means that there is nobody playing the guitar. Psi would be 0 everywhere. This is what we call a trivial solution, so that's not what we're interested in. So the solution we're interested in, somebody playing the guitar, must require that the sine of kl is equal to 0. But this sign is only equal to 0 when k times l is a multiple of pi. And here c is a natural number given the proportion of k and l and pi. So that means that the second boundary condition requires that the momentum, the wave number of the wave function, is a multiple of pi over L. So that means that the states are discrete. In this case, you can associate each number of k as defining a different state. So since every possible number of k defines a different state, that means that every value of c defines a different state. Since c is a natural number, we have a discrete number of states. Notice that we still have infinitely many states because c can be any natural number, but we only have a discrete number of states. So this is the mathematical point of view. The origin of the discretization, it's this requirement which came from the boundary conditions, which are the mathematical expressions of the wave confinement. And by the way, we require c to be a natural number because negative values of c would give the same state as its corresponding positive number. So for example, c equal 2 or c equal minus 2, they both describe the same state. So we require then that c is a positive integer number. So c must be a natural number. Okay, now let's turn our attention to a more phenomenological description of why the states are discretized in confined wave systems. So let's suppose we have a cosine wave. This is the spatial dependence of the cosine wave. Recall that k is the wave number, and the term inside the brackets, k times x, is the phase of the wave. So the wave number describes how the wave oscillates in space. So for example, at the origin, x0, we have k times 0, x0 is 0, which is 0, which means that the phase is 0, so the cosine of 0 is 1, we are at a peak. At the point x1, we see that psi is 0, which means that the phase is pi over 2. So in other words, k times x1 is pi over 2. At this point x2, we have that k times x2 is pi because the cosine of pi is minus 1. At x3, we have k times x3 equal to 3 pi over 2. And k times x4, another peak, we have that k times x4 is equal to 2 pi. And by the way, this distance it takes for the wave to experience a full oscillation is called the wavelength. So in our example, x4 is the wavelength. And from the condition that k times x4, in other words, k times the wavelength, is equal to 2 pi, we conclude that k is equal to 2 pi divided by the wavelength. Okay, so coming back to the role of the phase. We say that this term kx describes the phase accumulation due to propagation. So let's suppose we compare 2 points of the wave, the point xm and the point xn, and we ask what is the difference between the phase at xn and the phase at xm. So the phase at xn is given by k times xn. The phase at the point xm is given by k times xm. So the phase difference between these 2 points is given by k times xn minus k times xm. Now let's take a look at what happens when we confine a wave. So I'm representing as these purple dashed lines the walls of a box or cavity within which we're going to confine the wave. So the wave is confined within this box of length L. Okay, now let's choose a reference point X here, it can be any point, and let's follow the wave propagation as it propagates within the cavity, and we are particularly interested in finding how the phase changes, in other words, the phase accumulation as the wave propagates a round trip, in other words, as it propagates until the second wall, then is reflected back, propagates all the way to the first wall, is reflected back again, and comes back at the same point x. Okay, so let's suppose that the wave departs from x with this phase, and let's follow how the phase changes as it propagates. So until it reaches the wall, it will propagate as if it were in free space. So the phase changes like that, and then it hits the wall. So what is the effect of this wall? So this wall has two roles. One, it induces a phase, so the wave picks up a phase upon reflection. But we can ignore this effect, and I'm going to comment later on why we can ignore this effect. So let's focus attention on the second effect, which is to send the wave back. So instead of propagating as if it were propagating in free space, this oscillation will be mapped back into the cavity. For example, let's suppose that the wave is reflected from this wall, and we want to know the phase at the tip of the arrow. And let's suppose that the distance from the tip of the arrow to the wall is the same distance from the wall to the tail of the arrow. So the phase the wave will have at the tip of the arrow is the same phase the wave would have if it were propagating in free space and if it had propagated the same distance but in the opposite direction. In other words, the wall is mapping this phase back into the cavity, back at the tip of the arrow. So it's mapping this phase over here, it's mapping this phase over here, and so on. So that means that to know the phase the wave will have after it propagates a full round trip, we need to identify the total distance that the wave propagates in a full round trip and check the phase the wave would have if it had propagated this distance in free space. In other words, if we want to know the phase accumulation due to propagation in a full round trip, all we need to do is to find the total distance that the wave propagates in a full round trip. Since this distance is 2 times L, because the wave propagates twice within the cavity in a full round trip, then the phase accumulation due to propagation in one round trip is the same phase the wave would have accumulated if it had propagated a distance 2 times L in free space. So the phase at this point y, which is the point x plus 2 times L, is the phase that the wave will have when it propagates back into the point x. So after a full round-trip propagation, the phase at the point x is the same as the phase at the point y, which means that the phase accumulation, in other words, the difference between the phase at point y and the phase at point x, which is given by k times y minus k times x. So this is the phase at point y, this is the phase at point x. So since the point y is the point x plus 2 times L, it follows that the phase accumulation due to propagation in a full round trip is given by k times 2L. Now the total phase in a round trip is the phase due to propagation plus the phase picked up upon reflection from the walls. And I said a little earlier that we can dismiss the phase picked up upon reflection. And the reason why we can dismiss this phase is that the wave picks up a pi phase shift upon reflection from one wall and another pi shift upon reflection on the other wall. So since a 2 pi phase shift has no effect on the phase, we can dismiss the contribution of reflection from the walls. In other words, what really matters is the phase due to propagation, and this phase is k times 2L. Now let's check the consequence of confining the wave in a cavity. So we start at point x, which has phase kx. After one round trip, the phase at point x will be the original phase plus the contribution of spatial propagation in a round trip. So we have k times x plus k times 2L. After two round trips, we pick up another phase shift of k times 2L, so we get kx plus k times 4L. After 3 round trips, the phase at point x will be kx plus k times 6L, and so on. But these are the same point x, the same point. So we are saying that the phase at the point x is k times x, and we are also saying that the phase at the same point x is kx plus k times 2L, and the phase at the same point x is kx plus k times 4L, and so on. So how can that be if that is the same point x? We can only ascribe one value of phase to the point x. So that means that this term k times 2L and this term k times 4L and this term k times 6L and so on, they must all of them be a multiple of 2 pi. Otherwise, we would be ascribing different values of phase to the same point x. So we need to require that all of these terms be a multiple of 2 pi, and this is called the requirement of self-consistency, which means that the phase at a specific point but must be consistent. It must have only one value. It cannot have multiple values. And notice that this condition that all of these terms must be a multiple of 2 pi boils down to the condition that this term must be a multiple of 2 pi. If this term is a multiple of 2 pi, then it follows automatically that all the others are also multiples of 2 pi. So the requirement of self-consistency boils down to the requirement that k times 2L be a multiple of 2 pi, so c here is again a natural number. So we reach the same conclusion as before. The allowed wave vectors of the system are multiples of pi over L. Different c's specify different wave numbers and hence different states of the system. So we have reached again, using the requirement of self-consistency, the same conclusion that we had reached using the boundary conditions. In both cases, we found that the states are discrete because the allowed wave vectors must be multiples of pi over L. Now, to gain further insights into the meaning of these 2 points of views, let's suppose that the wave is electromagnetic in nature and that these 2 walls are perfect mirrors. So the mathematical point of view means that if we try to solve Maxwell's equation inside the cavity applying the corresponding boundary conditions, then we will find that the only solutions to the problem satisfy this condition. So the mathematical point of view is telling us that all physical solutions to the problem satisfy this condition. As to this requirement of self-consistency, one way we can understand it is as a requirement that when the wave interferes with itself, in other words, when the wave propagates a full round trip and comes back to the same point, then this interference must be constructive because the wave will have accumulated a multiple of 2 pi. If this interference was not constructive, if this phase was different than a multiple of 2 pi, then the wave would interfere destructively with itself and disappear. So this is, of course, a phenomenological description. The more rigorous description is the mathematical, which is stating that the physical solutions must satisfy this condition. So the two ways complement each other. It's important to understand both the rigorous way and the more intuitive phenomenological approach. But now let's move on to a very important application of our conclusion. And this is the problem of an electron confined in a quantum well. So a quantum well is just a fancy term for box. So in our problem, we have an electron confined in a box. And since in quantum mechanics electrons are described by wave functions, we have a wave confined in a box of length L. So that means that the self-consistency requirement applies. And that means that the allowed wave numbers are given by multiples of pi over L. So in this problem, we're going to begin with the allowed wave numbers, and we're going to find the energies of the electron when the electron is confined in a quantum well of length L. So to find the energy from the wave number, we need to use the famous de Broglie formula, which relates the mechanical momentum P with the wave number K through Planck's constant h. So this is the de Broglie formula. And if we have already established that the wave number is discretized due to the self-consistency requirement, it follows that the momentum is also discretized. So when an electron is confined in a quantum well, it cannot have any momentum. The momentum the electron can have when it is confined in a quantum well is a multiple of Planck constant divided by 2 times the length of the cavity, the length of the well. So these are the allowed momenta of the electron inside the quantum well. Now, to find the energy, we can recall from classical physics that the kinetic energy is connected with the momentum through this expression, where m is the mass of the particle. In this case, m is the electron's mass. So since the allowed momenta are discrete, it follows that the allowed energies are also discrete, and to find these values, all we need to do is to use this expression in the expression we obtained from classical physics. So if we do that, we find that these are the allowed energies of the system electron confined in a quantum well of length L. And recall that each value of C indexes a different electron state. So C equal 1 indexes one state, C equal 2 indexes another state, C equals 3 indexes another state, and so on. And once we have specified the state, in other words, once we have specified the number C, then we have specified the energy of the electron, which is given by this expression. So this is a very important result, and we're going to use it many times in our course. But for now, we're going to conclude this lecture, and in the next time, we're going to look at the notion of equilibrium. So I see you the next time. Bye bye.